Welcome to this explainer. Okay, I want you to go ahead and put your engineering hats on with me today because we're looking at the ultimate troubleshooting guide for the largest, literally the most complex machine humanity has ever built, the electrical grid. I mean, think about this. If you strung all the world's transmission cables end to end, they would stretch 42 million miles. That is almost halfway to the sun. For decades, this massive physical architecture has just quietly powered our lives in the background. But right now, it's facing an unprecedented system shock. We are fully entering the age of artificial intelligence, and man, AI is incredibly power hungry. So to keep up, we urgently need to upgrade this 42 million mile behemoth. Okay, let's dive into this. Here is our system diagnostic blueprint for today. 1. System check, the legacy grid. 2. Overload, AI and data centers. 3. Capacity patch, superconductors. 4. Stability patch, synchronous compensators. And finally, 5. Global scaling. Let's get right into it. Section 1. System check, the legacy grid. To really troubleshoot the grid, we first have to understand this fundamental feedback loop of the modern world. There is a direct, undeniable relationship between the energy an economy consumes and its economic output. Basically, the richer you are, the bigger your grid. And the bigger your grid, well, the richer you become. Looking back at the historical timeline, we saw this nonstop explosive expansion in the early 20th century. By 1930, 70% of U.S. homes were electrified. But then the system dynamics kind of shifted. The oil crisis in the 1970s forced utilities to pivot from this dig we must mentality to save a watt, pushing really heavily for energy efficiency. Add in a shift toward, less manufacturing and a lot more office work in Western countries, and by the 2000s, electricity demand basically flatlined. Now, that was great for a while, right? We kept growing our economy without actually burning more power, but it caused a hidden problem. When you stop building, your supply chains atrophy, your workforce ages out. The Western world literally lost its muscle memory for building massive electrical infrastructure. Let's move to Section 2, Overload, AI and data centers, and see how this builds. Because that era of flat power demand we just talked about, yeah, it's officially over. We're dealing with a sudden, massive system shock hitting our legacy grid architecture today. We are seeing a three-pronged surge in demand right now. First, we're transitioning from gasoline cars to EVs. Second, we're swapping oil and gas boilers for electric heat pumps. But the real heavyweight here? Artificial intelligence. AI requires these massive data centers that just absolutely guzzle electricity. Because of all this, the world is predicted to use twice as much electricity by 2050. Let that sink in. That is an entire new USA's worth of electricity every 5 years. To put it in perspective, AI alone could boost the global economy by 15% over the next decade. But by 2030, it could consume as much power as the entire country of Japan. Now, what's really interesting is this staggering number, $300 billion. That's the amount of money just 4 major tech companies intend to spend this year alone on AI infrastructure. They are pouring capital into this transition, but here's the catch. All those data centers are completely useless if the physical grid can't deliver the electrons to actually power them. And this brings us to a pretty harsh geopolitical reality regarding our hardware. The stark contrast is fascinating. The U.S. has barely seen an uptick in power generation since 2000. China, however, they've increased their power generation 7 times over in that exact same period. Because they kept manufacturing, their supply chains and their skilled labor pools are incredibly robust. Energy is destiny, folks. If you cannot build out the grid to power new industries like AI, you simply will not be a competitive economy in the 21st century. Section 3. Capacity patch. Superconductors. So how do we fix this transmission bottleneck in countries where the grid hasn't grown in literally decades? We can't easily build millions of miles of new, bulky wire. We need a major hardware patch. Now, as engineers, we know the eternal enemy is resistance. Pushing massive power from a plant to a city means unacceptable energy loss through standard materials. But the holy grail here? A superconductor. This is a special class of materials that, under certain extreme operating conditions, allows electric current to pass through with absolutely zero resistance. Let's look at a direct comparison. Legacy copper or aluminum cables are decent conductors. They have relatively low resistance, but they still lose energy, and pushing more power through them requires massive physical space. Superconducting cables, on the other hand, like those being developed by a Microsoft-backed startup called Veer, have zero resistance. They can carry an insane amount of power in a very, very compact space. One of these cables could essentially replace several conventional transmission lines. It's a real game changer. Of course, there's always a catch. right? To reach that zero resistance state, the material has to be kept extremely cold. We are talking 77 Kelvin, achieved using a continuous flow of liquid nitrogen. That is colder than the dark side of the moon. Right now, Vertis is successfully manufacturing these in 10-meter sections. It's an intense logistical hurdle, requiring vacuum tubes and constant cooling. And electric utilities are famously conservative businesses, so adopting this quirky engineering isn't going to happen overnight. But the incredible power density means superconductors might just be the unavoidable future of transmission. Section 4. Stability patch, synchronous compensators. Because capacity is really only half the battle. The grid must be perfectly balanced, second by second. Supply must exactly match demand. If it doesn't, things get disastrous very quickly. And this brilliantly illustrates what happens when that delicate balance fails. The results are catastrophic. Take the recent massive Spanish blackout, for example. Step 1. Several solar farms in southern Spain unexpectedly went offline. Step 2. A sudden imbalance between supply and demand hit the network. Step 3. Voltage spiked, which forced grid components to automatically disconnect to basically save themselves. It created a cascading domino effect that plunged tens of millions of people into darkness and wiped an estimated 400 million euros right out of the Spanish economy. The secret to that balance has always been mechanical inertia. Traditional power plants, coal, gas, nuclear, they all use massive, heavy, rotating generators. Those spinning turbines provide physical inertia. They're essentially mechanical shock absorbers. If a power plant trips offline, these heavy turbines keep spinning for a moment, injecting just enough emergency power into the grid to keep the voltage stable while the entire system recovers. But here is the modern grid paradox. Spain had recently tripled its solar power. Now, solar is fantastic, it's cheap, it's clean, but solar panels convert sunlight directly into electricity with zero moving parts. No spinning generators means absolutely zero inertia. So when those solar farms dropped offline, the grid just didn't have that mechanical safety net to catch the fall. To fix this, power companies like Statkraft are utilizing a beautifully brute force piece of engineering. Just listen to these specs. It weighs 100 tons. It's spinning around at 1500 RPM. So the crucial point is the synchronous compensator. It acts exactly like the giant spinning turbine you'd find inside a coal or gas plant, but it doesn't burn any fuel. It doesn't generate net new power. Its only job is to spin. By deploying these 100-ton spinning behemoths onto the network, you artificially inject that much-needed physical inertia back into the system, perfectly stabilizing a modern grid that relies heavily on renewable solar energy. Section 5. Global scaling. Now, deploying supercooled nitrogen cables and 100-ton spinning compensators is incredible for the US, Europe, and China. But as we look at fixing the world's biggest machine, different parts of the globe require completely different architectural approaches to upgrading their grids. When we look at architecture, traditional macro grids cover thousands of square miles as massive national infrastructure. But for areas beyond the reach of the main grid, a completely new architecture is thriving: the mini-grid. Companies like Husk Power are building localized solar mini-grids in places like Nigeria. These serve small areas, maybe just a single village or an island of about 400 people, bringing piecemeal, reliable 24/7 power right where it's needed, without having to wait around for a massive national transmission line. This is absolutely vital because roughly 565 million people in sub-Saharan Africa still lack access to electricity. Mini-grids are changing that, powering everything from evening homework to local rice milling machines. And it's scaling up fast. The World Bank is backing Mission 300, which aims to connect 300 million people by 2030. It's actually highly reminiscent of the US rural electrification of the 1930s. Every giant grid starts small. Eventually, these isolated mini-grids will interconnect like building blocks to form massive, resilient national networks. Which leaves us with this final thought. Energy truly is destiny. The grid is the unsung hero of modern civilization. And right now, the sheer demands of AI and massive data centers are pushing this aging hardware to its absolute physical limits. From liquid nitrogen superconductors to massive spinning compensators and rural mini-grids, the engineering solutions are out there. The question is, will we upgrade the world's biggest machine fast enough to win the future? Thanks for exploring this explainer with me.